Hello everyone, myself Rachana. I am a PhD fourth year student. Today I'll talk about estimating the black hole masses of narrow line Seyfert galaxies using damped random walk model. So I'll give you a brief introduction of what exactly is AGNs. So AGNs is a active galactic nuclei is basically this compact region at the center of the galaxy and which emit in the entire range, we'll say start from radio to all the way up to gamma rays, and shows broad range of luminosities from 10 raised to power 42 hour per second to 10 raised to power 46 or 47 hour per second. Further, they show strong and broad optical and UV emission lines. You can see here as well that the Lyman alpha, all broad lines are there like H alpha or so. So further, they also show this continuum variability, and along with that, this line emission variability. This is just these few properties of AGNs. Further, as I told you that these particular galaxies in general emit in all the electromagnetic spectrum. So because of that, they got a big classification. The classification can be understood in this one particular image where I am showing the unification model. So in this unification model itself, we can see all the classes of AGNs. And as we already see some of the jets, but in different contexts. Here, if you see a jet, then these are radio loud radio loud AGNs. And if you do not see a jet, then these are radio quiet. Further, based on the orientation effect itself, these two classes further got classified into multiple classes. I'll not go into those classes, but go in this particular class, which is Seyfert 1. Started from mainly 5 degree to let's say 45 or 50 degree, and you will see this compact region where you see both broad and narrow lines. So spectrums of this particular class is seen here. This particular class itself got divided into two main categories. One is broad line Seyfert 1 galaxies, and another one is narrow line Seyfert 1 galaxies. They started classified into mainly they mainly classified because of two lines. First is this particular line H beta, and the second one is the flux ratio of O3 by H beta. So in NLS1's narrow line Seyfert 1 galaxy I am talking about, in NLS1's the FWHM of this H beta line is lesser than 2000 km per second, and in broad line it is higher than 2000. So other one is the flux ratio is lesser than 3 in NLS1s. So just this particular class got characterized because of these two lines, but the property they show are very peculiar, very for example, the Fe2 strength in this particular class is very strong. They show very strong Fe2 strength in the UV region as well and in optical region as well. There is very less sample in UV region, but in optical this is very well studied. Another thing is that they show very high, they actually accrete at Eddington limit and harbor low mass black hole. Now this particular property of having low mass black hole, the masses estimated here is mainly because of virial mass. If I'll tell you that the mass estimation, as we know, the virial mass, simply the mass is equals to mv square, the simple formula. From there, the v square part is coming from the FWHM of this H beta line. And since NLS1 has smaller, the FWHM is lower than 2000 km per second, they can get low mass black holes compared to BLS1. So in numbers, if I'll talk about, NLS1 has mass of 10 raised to power 6 to 10 raised to power 7 or up to 8 solar masses, but BLS1 can go up to 7 to 9 solar masses. So this particular property of low mass black holes questioned a lot. Why? Because first the question came when Fermi-LAT actually detected gamma ray narrow line Seyfert 1 galaxies. The masses of these particular class, gamma ray emitting narrow line Seyfert 1 galaxies, conducted by Kale et al., where what they did is that they fit accretion disk modeling, the SDSS light curve, and fit it to it and find out the mass of it. The mass they got for NLS1s, which we till now seems to be lower masses, 6 to 8. Now they got up to 10 raised to power 8 to 9 orders. Second study almost on the same concept done by Gayatri et al., and they also conclude the same thing, that NLS1s in radio loud or radio quiet has the masses equal to their counterpart, which is broad line Seyfert 1 galaxy. So the question here arises are something is there, is this particular class actually has higher mass black holes, or it's just something that we do not know. So again, another concept is also also studied by spectropolarimetry observation as well. But the thing is, this is only one source. But again, Bell et al. Found out that mass of this particular NLS1 is 10 raised to power 8. So this entire thing motivates us to find out the mass of black holes of this particular class, Narrow Line Seyfert 1 galaxy, but in a different aspect. So what we did, we didn't use H beta, or because H beta can be influenced by the obscuration as well. If we see the AGN as an edge on or face on, then we can clearly the H beta can be obscured, or the H beta can be lowered if you're saying the face on as well. So rather than using this, what we use is to use light curves. Light curves, I'm just showing you here, and I want you to just focus on this particular part. We are using the light curves of this particular class, and we are using G band light curves. And we are fitting the damped random walk model. How exactly we are fitting the AGN light curves? We use this particular covariance matrix. Here, the main two parameters you are saying is sigma and tau. Sigma is the variability amplitude, basically this particular part, the amplitude of the light curve you are seeing, and the second one is the variability time scale, the time scale at which the AGN is kind of quasi period. So these two parameters are very important while fitting the AGN light curves. So how exactly we are doing this? We are using Celerite model, where we are fitting this damped random walk model, and we are using this kernel function which correspond to the structure function. In simple words, if I'll say, in light curve, if two epochs, how they are behaving with respect to each other will give you this kind of structure function. Now, if those time scales in time frame, if we change to the frequency frame, we'll see this kind of power spectral density. Now, the AGN of the PST of an power, the PST of any AGN can be seen something like this, where this particular flat part is white noise, and the slope correspond to power -2 is the red noise, which is the smaller frequency, or we can see where the noise part of any light curve. But this particular part will probe the damping time scale. So this flat part, or the white noise part and red noise part, got distinguished at this particular frequency, which we call break frequency, which again which if you invert it to 1/2 pi tau will give you the damping time scale. Now the point is, this damping time scale people have studied to find out the mass of black hole. Now another thing is that by the baseline of light curve I showed you, we took that particular baseline 10 times of this damping time scale, so that we can probe this white noise part accurately. We'll go further, and then we use GTF light curve, which provide two kind of light curve. One is archival data that we can see directly from the site, and another one is the requested data, which is force photometry data. So since this is a transient facility, there is multiple intranight epochs as well, but with no doubt with a higher uncertainty. But in case having higher number of epochs will help us to fit DRW model very efficiently. So we use both the data, forced and normal. Normal, I'm saying the archival one, and forced that we requested them source by source for a sample of 5,600 sources for both the sample. Now here the point that I'll focus is this: both the samples, we pick NLS1 sources first and then controlled BLS1 sample, so that we can compare the properties of two. But the entire DRW model we run for around 5,000 sources in both the cases, and filtered out on the way like how exactly DRW model is fitting. How many epochs are there? Is this baseline is significant enough, noise and all, and the AGN like variability is there or not? these parameters, the final sample that we got is around 1100 sources, which is again comparable. So this particular control has been done in luminosity redshift plane. We also see that our final sample is also in controlled LZ plane. So this is a good thing here. So I'll show you this, that this is kind of one of our samples, like the last final sample of DRW model, and where this orange curve is the fitted PST, power spectral density, and along with that we also fit broken power law, which is also AGN DRW fitting model, we can say, and both are like consistent enough in our final sources. Again, as I told you that there is two kind of photometric that we are dealing with in GTF. One is normal photometry. You can see the power spectral density is not probing the white region part very well, and it's kind of giving red noise part equivalent to it. But if you see here, then PST is very well sampled, because the force photometric data consists more epochs. We are now kind of dealing with the higher number of epochs or higher uncertainty. So whenever the PST is not probing the white noise part, or it's kind of flat PST, then we are going for a force photometry to see what how exactly the PST is fitting or not, and we see that this is clearly fitting. So we did our analysis in both way. Further, let's go to the next part, which is damping time scale. As I told you, the damping time scale is related to the mass. Burke et al. In 2021, he studied this one, and our BLS1 sample is kind of agreeing with the fact, but NLS1 sources, the lower mass ones, are not agreeing with this. The damping time scale is kind of overestimated. This is SS model or Sakurai model or thin disk model that we can say. Here in their paper, what are they trying to do is that damping time scale we can find out the mass. In here, the same thing is there. But as this is overestimated, there is another thing we need to know. What is it? So here the mass is obviously overestimated because of it, because the tau is overestimated, hence mass will be. But they didn't take into account, which is what? The Eddington ratio. So if we see this Eddington ratios as well, because NLS1 has higher Eddington ratio, so this value will give the tau DRW to be overestimated, and hence mass will be overestimated. So if you take into account that the R Eddington, you will take this R Eddington or Eddington ratios into account, then what will we get? We get the clear distinction between these two histograms, which is previously are onto each other. That means previously NLS1s are showing that the masses may be exactly equal to their counterpart, which is BLS1, and maybe between 7 to 9. But if we incorporate the fact that Eddington ratios may influence your results, this will give you their clear distinctions. Yeah, so no doubt there is the entire mass difference is there, but the point is the mass of NLS1s and BLS1s is clearly different from each other. Yeah, so to find this, not only we just incorporate R Eddington directly, as R Eddington is simply bolometric luminosity by Eddington luminosity, which can intrinsically influence your volumetric luminosity. So rather going into that factor, we choose two other modes two other relations as well for our sample. What we assume that, let's say BLS1 has true virial masses, and based on that we found the correlation between Eddington ratios and Fe2 strength. This particular correlation we used to find out the mass of the black hole. So we didn't directly use Eddington ratio, rather we're going for the Fe2 strength, which is not using the mass of the virial mass approximation. So our results are not influenced because of that. Secondly, we also use DH beta parameter, which is a kind of shape indicator, and if we use that as well, our results are something like that, where this is clearly distinct from each other. So using both the equations, the NLS ones are on the lower side of the lower masses in Seyfert 1 galaxies, and BLS ones has higher masses, which is clearly seen from here. In summary, if I'll say a narrow line Seyfert 1 galaxies, as Bucketall said that that the mass, you can find out the mass directly from the damping time scale, which is not actually true. You have to take care of Eddington ratios as well. Secondly, we already know that virial masses can be influenced from all other factors, but this damped random walk is not at all influenced by those terms. So we can say that these results, which is lower masses black hole, is consistent with the virial mass black hole. So this is fine to say. Third thing is that we all know that in estimation, mass estimation, reverberation mapping is one of the clean methodology. But for estimating that much of the number, like 5,000 or 6,000, it's kind of very time consuming job. So, but for the true masses, if we'll go for at least for 100 or 200, if we can find out the mass of these classes, that will be great. So reverberation mapping can find the true mass of black holes. So yeah, so this is all for my talk. Sorry for taking that much of time. Yeah, thank you.
Thank you. So did you do any statistical test to see whether these two histograms actually are from different samples, or like, to quantify what you were saying, that the black hole masses have a different, peak?
I am sorry, I didn't get.
So the two histograms that you were talking about, where you were trying to see see whether the peaks are at different values or at the same values. So I was asking whether you have done any statistical test, like the Kale's test, to see whether these two populations are drawn from the same parent population, or some quantification of the.
Yeah, so you are saying that in the BLS one itself, if these are statistically same or not. So no, actually no, because so we tested it, but it's not. So that's why I said this is kind of, the entire DRW is kind of off. There is an offset in the masses. So the point here is, I want to underline, is that for one source, if you go, then DRW cannot say that this is the final mass of it. But for the entire sample of source, then you can say that, okay, for entire sample, if it is showing on the lower side, then it must be, it is on the lower side. For one sample, it will not gonna justify. Again, the BLS one itself is not corresponding to it. The case test we tried, yes.
Okay.
Yeah.
Any other question? Yeah.
Yeah, so same in this histogram. So I understood from the cartoon you earlier presented that this narrow line, broad line is basically depends on from where you are measuring your emission, right? So here this black line, which corresponds to broad line.
Yes.
Right? Broad line is falling on this pink shaded thing, which is also narrow line.
Right.
So what does it mean, Mane?
Right. So this is an offset in DRW estimations. That is what I'm saying. So if you see if you go for the black comparison, then it is kind of an offset itself.
Offset.
Yeah. So if we'll say that the virial mass is true, I said if the BLS ones, we'll assume that in BLS one the virial mass estimations are true masses.
True mass. Okay.
Right.
Okay.
So the DLW masses are on the offset of it, like it's kind of on the lower side of it itself.
Oh, so this is irrespective of any sample.
Right. It's irrespective of any sample. Even if, so there is two sample for now. One is Rakshit 2012 and another one is Vedhai's 2017. Both the samples showing the same.
But in these samples, there may be oh no, it is not possible. Right. It is not possible that one black hole lies in both sets. It's not possible, of course, right? No. Yeah. Even.
So it's just an offset in the DRW model. Yeah. So one another thing that we found out as well. So every time you increase this baseline, it will improve. The DRW is actually improved a lot. So this is bare minimum what we have, because right now it's just 2000 days of time scale. So if you go for higher masses, right, that in what we are having in BLS1s. So BLS1s actually have a sample of higher masses as well. But for higher masses, what we in light curves, what we will see, higher damping time scales. Higher damping time scales need bigger baseline. But GTF only had 2000 days of timeline, so that will restrict itself to low mass black holes. So in BLS1 itself, we are on the lower side of the masses. So that is again, so as the ZTF will give new and new the data, like from 2018 to now, and whenever the data will release, will improve this model. Yeah.
Which of the actors are more favorable for estimating the correct?
So
believed.
yeah, so the broad line will shift to the rightwards, because as we go for bigger baseline, we'll go for higher damping timescales and higher masses. So now the entire shift will on the righter side, and it will approach to virial mass itself. So this offset will further reduced.
Any other question? If not, then let's thank her and all the speakers of this.